Yeah, it says it is online.
It's on now? Yeah, it's on.
Yes, okay. So,
Check it
shall we
once.
start?
Yeah.
Check it once. Someone should check, please.
No, I
It
don't
is
see
online.
it.
It is online. Kindly proceed.
Okay.
Live streaming, right? Yes. Yes.
Okay.
Okay.
So we'll start then. Good
Yeah.
afternoon, all. Welcome to the weekly online lecture series, which is jointly organized by Savitribai Phule Pune University and South Asian Meteorological Association, SAMA. So we are on the 13th lecture today, and this lecture will be delivered by Professor C.A. Babu from CUSAT, who is retired from there, on vorticity equation in Cartesian coordinate, scale analysis of vorticity equation, relation between cyclonic, anti-cyclonic, vorticity, advection. Before we proceed with the lecture, I would request Professor Someshwar Das sir, who is Secretary SAMA, to please give welcome address.
Thank you very much, Dr. Rohini. Good afternoon, everyone. We welcome you on behalf of South Asian Meteorological Association and Savitribai Phule Pune University, India. You have already heard Professor Babu last week, and he teaches quite slowly, and so it is very easy to understand his lecture. And today's lecture is on a very important topic, as you know. It's about the vorticity equation, advection of vorticity, cyclonic and anticyclonic vorticity, which are so important for the development of the baroclinic systems, barotropic baroclinic systems, both advection as well as the vorticity are very, very important parameters. So how you derive them, the equations, those things will be explained today in today's lecture by Professor Babu. He has already been introduced last week, so probably today there is no need for his introduction. But he has been teaching dynamic meteorology for quite some time at Cochin University of Science and Technology. So he has a lot of experience. In fact, he initially proposed to conduct this online lecture series, on dynamic meteorology all by himself. That was the source of inspiration to start this lecture series as soon as possible. So, as you know, we have had many experienced professors and scientists who have delivered lectures so far, as per the practice of SAMA. The resource persons are very senior persons, both from academic field as well as from the research organizations. Also, this lecture series, as you know, is meant for people who are interested in learning atmospheric dynamics and its applications to climate sciences. Because most people, they just work on climate change, but they don't have the fundamentals of the physics and dynamics of the atmosphere. So this is one of the important topic for that matter. Already we are late by about 10, 12 minutes, so I will not take much time. So enjoy the lecture, and as usual, you can ask the questions in the question and answer box, and it will be answered by a speaker at the end of the talk. And all the lectures are also available on the YouTube. We are getting good hits. Yesterday, I received a mail from YouTube that last month the highest hit was Professor Bhaskar Rao's lecture. That was the 8th lecture of this lecture series. So I'm going to share that clip maybe with all the SAMA members soon. So thank you very much and enjoy the lecture. Have a good day. On to you, Dr. Rohini.
Thank you, sir. So now I request Babu sir to please share his screen and start with the lecture.
Welcome to the Atmospheric Dynamics online lecture series of SAMA. Today, I am going to discuss fundamentals of Vorticity and Vorticity equation. And in the basics of Vorticity, I would like to explain scale of velocity, relative vorticity, shear term, curvature term, planetary vorticity, absolute vorticity, potential vorticity, and their equations. After that, I would like to discuss vorticity theorem and vorticity equation, significance of different terms in the vorticity equation, potential vorticity, that is potential vorticity equation, CAV trajectory, that is barotropic vorticity equation, scale analysis of vorticity equation, and relation between vorticity, advection, and divergence. So let me start. Vorticity is the microscopic measure of rotational tendency. In general, measure of rotational tendency is assessed by scale of vector V, that is del cross V, where vector V is vector wind in the three principal axes. That is vector V is equal to U along unit vector I plus small letter v along unit vector j plus W along unit vector k. Hence, del cross V provides velocity in the principal axes x, y, and z. Since vector v is relative velocity of air parcels, del cross v is referred as relative velocity. The velocity of air parcels produced by the relative motion of air with respect to air surface in the three principal axes. Since vertical component of velocity plays vital role in the weather processes, meteorologists are concerned with velocity in the local vertical, that is z-axis. The relative velocity in the vertical axis can be evaluated as unit vector dot del cross v and is dou v by dou x minus dou u by dou y by expanding del cross v as determined ijk dou by dou x dou by dou y dou by dou z and uvw as indicated in the determinant. The vertical component of relative velocity is expressed as theta, Greek alphabet theta, and its unit is s raised to minus 1. Cyclonic velocity is considered positive and anticyclonic velocity is considered negative. We can evaluate rotational tendency over a station in the vertical direction from the wind pattern. Let us consider 4 stations over a region in a polygon array using the equation theta is equal to dou v by dou x minus dou u by dou y. The stations are in the wind vectors at the stations A, B, C, and D are indicated in the diagram. And the wind components can easily be resolved as small letter e is equal to minus f of sine ddd and small letter v is equal to minus f of cosine ddd, where f of is the magnitude and ddd is the wind direction as per the meteorological convention. The wind components for the velocity equation theta are represented as wind vectors at the stations A, B, C, and D. Accordingly, dou v by dou x is equal to v suffix b minus v suffix d divided by delta x, and dou u by dou y is equal to u suffix a minus u suffix c divided by delta y. It is obvious that the air parcels over the region ABCD has an anticyclonic velocity for the given region with polygon position A, B, C, and D, because here the wind vectors are prominent in the anti-clockwise direction. It is microscopic measure of rotational tendency. Anticyclonic velocity gives rise to sinking motion near the surface of a desert. For example, Thar Desert in Rajasthan or Sahara Desert in the North Africa, warm and dry air prevail most of the time due to sinking motion caused by anticyclonic vorticity and divergent wind. On the other hand, cyclonic vorticity, that is anti-clockwise rotational tendency, prevails in the low pressure system. The general low pressure systems are low pressure area, depression, deep depression, tropical cyclone, monsoon depression, mid troposphere cyclone, offshore vortex, extratropical cyclone, thunderstorm, nor'westers, elongated low pressure system associated with monsoon cloud band, tornado, water spout, etc. Cyclonic vorticity gives rise to ascending motion. This initiate cloud processes and subsequent precipitation. Next, let us discuss the rotational tendency initiated by the rotation of the Earth. The Earth rotates in its own axis from west to east at an angular velocity of rotation omega, that is 7.292 into 10 to minus 5 s to minus 1. We have seen that any object in the rotation at omega has a vorticity of 2 omega. That is, vorticity is twice angular velocity of rotation. Since meteorologists are concerned with rotation in the vertical axis, let us resolve omega into omega z. That is component of omega in the z axis. Omega z is equal to omega sine phi, where phi is the latitude of the station. Therefore, planetary vorticity small letter f is equal to 2 omega sine phi. Thus, we have two different types of vorticity. One is due to motion of the air parcels in the atmosphere or due to relative motion, and is known as relative vorticity. And the relative vorticity can have cyclonic and anticyclonic nature according to its nature of rotation. On the other hand, the planetary vorticity, that is the rotational tendency induced by the rotation of the Earth, has always cyclonic vorticity, and it is minimum in the equatorial region and zero at the equator, and maximum in the polar region, and maximum value is at the poles and is twice angular velocity of rotation of the Earth, that is 2 omega. The relative vorticity theta is contributed by two factors, that is shear term and curvature term. The rate of change of wind normal to the direction of flow produces shear vorticity, whereas turning of the wind along a streamline gives rise to curvature vorticity. The equation for the relative vorticity in Cartesian coordinate system is unit vector k dot del cross v is, and it is theta is equal to dou v by dou x minus dou u by dou y, and it provides rotation tendency in the local vertical without specific components in for the shear term and curvature term. Let us use equation for vorticity in natural coordinate system to describe the components. Theta is equal to minus dou v by dou n plus v divided by r suffix s to express the relative vorticity as the sum of shear term, that is minus dou v by dou n, and curvature term v divided by rs, where r suffix s is the radius of curvature of the streamline. Natural coordinate or TNK system is closely associated with the flow pattern in the weather charts, and numerical values of shear term and curvature term can easily be evaluated from the weather charts with the help of the curvature grid. Next, let us discuss fundamental features of flow pattern. A straight line flow can have relative vorticity due to shear term even though value for the curvature term is 0. On the other hand, a curved flow may have 0 relative vorticity provided that shear vorticity is equal and opposite to curvature vorticity. Next, let us examine nature of relative vorticity for a straight line flow associated with monsoon cloud band in the Arabian Sea centered around 15 degree north. You can see the diagram. Outline of India is represented. In the western side, you can see Arabian Sea, and 15 degree north latitude is indicated. And in the northern side of 15 degree north is a region A, and southern side region B. In the region A, the relative vorticity is positive as per the equation, indicating cyclonic vorticity, even though the flow pattern is straight. Similarly, in the region B, we have anti-cyclonic vorticity as per the equation, even though we have straight line flow. Next, let us discuss or let us derive vorticity equation. For this, consider x and y components of momentum equation in the Cartesian coordinate system in the expanded form. And in the first equation, 2 omega w cosine phi is not considered for the derivation because it is small compared to the other terms. And we are interested in the vertical component of vorticity in terms of theta and f, and theta is dou v by dou x minus dou u by dou y, and hence we simplify the equation accordingly. Let us take partial derivative of second equation with respect to x and subtract partial derivative of first equation with respect to y. After simplification and rearrangement, we get the vorticity equation, that is d by dt of theta plus f is equal to a divergence term plus a tilting term plus a solenoid term plus a frictional term. So, vorticity theorem, the above equation is a mathematical representation of vorticity theorem. Vorticity theorem states that the rate of change of absolute vorticity of a group of air parcels following the motion is contributed by a divergence term, tilting term, solenoid term, and frictional term. Next, let me start discussions on physical significance of vorticity equation. The first term in the RHS of the vorticity equation is minus theta plus f multiplied by capital D. Capital D is the divergence, is called the divergence term. It is fluid analog of the contribution to absolute vorticity which arises due to change in divergence. Since no divergence for solid, this particular term does not arise for solid. When divergence occurs, effective area of air parcels increase, crossing decrease of vorticity, that is d by dt of theta plus f is equal to minus theta plus f multiplied by d. When d is positive, because of minus sign on the RHS, the term d by dt of theta plus f decreases. Thus, divergence causes decrease of vorticity. On the other hand, convergence increases the value of vorticity. Now, let us start discussion on the physical significance of tilting term, that is second term in the RHS. To understand the physical meaning of this particular term, let us consider a wheel with a horizontal axis at the beginning as indicated in the diagram. Let us consider the first term, that is dou w by dou x multiplied by dou v by dou z. So at present, the wheel has fixed in an axle oriented in the east-west direction and is rotating anti-clockwise as indicated from west. That is, when dou w by dou x is less than 0, the vertical velocity w decreases towards east as indicated in the diagram. So the west end of the axle moves up and east end lowers as indicated in the diagram. The rotation of the wheel turns gradually to become in the horizontal as the axis turns vertical. Thus, a cyclonic rotation about the vertical will appear during the course of time. So, this is a transformation of relative vorticity in the x-axis into z-axis by the peculiar wind pattern existing over the region. Thus, increase of theta plus f occurs as minus dou w by dou x multiplied by dou v by dou z is a positive quantity in the given situation. That is rotation in the anti-clockwise direction. Similarly, the second component explains transformation of relative vorticity in the y-axis into z-axis. Since the term deals with the vorticity transformation from the horizontal axis into vertical, it is referred as tilting term or tipping term. Next, let me explain the physical significance of the third term in the vorticity equation. The third term in circulation theorem, it was already seen. It is solenoidal term. We have already seen that minus closed integral dp by rho is equal to minus closed integral in bracket alpha dou p by dou x dx plus alpha dou p by dou y dy, where rho is the density and alpha is the reciprocal of density. Alpha is the specific volume. By Stokes' theorem, a line integral can be converted into surface integral, that is area integral, where delta A is an area element within the curve. That is minus closed integral alpha del p dot dr is equal to closed equal to area integral unit vector k dot del cross in bracket minus alpha del p dot dA. And we have already seen that unit vector k del alpha cross minus del p is equivalent to a determinant with first row elements I, j, k and second row elements dou alpha by dou x, dou alpha by dou y, dou alpha by dou z, and the third row elements minus dou p by dou x, minus dou p by dou y, and minus dou p by dou z. And the above equation has an area directed out of the plane in accord with the right hand rule. This is circulation about an area. Thus, vorticity is equal to circulation by area. This term contributes the generation of vorticity by the solenoid, that is baroclinicity of the atmosphere, that is inclination of isobaric and isosteric curves. The solenoid term does not exist in the vorticity equation in isobaric coordinate system, as density or specific volume is a function of pressure, and hence vorticity equation in isobaric coordinate system is similar than that in the Cartesian coordinate system. The solenoid term does not arise in a barotropic atmosphere because the isobaric and isosteric curves are coinciding in a barotropic atmosphere, and hence we need not expect any circulation or vorticity due to the solenoid time. The last term in the vorticity equation represents the effect of other forces such as friction, that is turbulence and viscosity. If the frictional force exerts a torque-like action upon fluid elements, a change of vorticity is observed. In most of the applications, additional forces are small and can be neglected. When the horizontal divergence is small, no vertical motion takes place and other terms are also small, the vorticity equation becomes d by dt of theta plus f is equal to 0. Here, as you know, horizontal divergence is fractional rate of change of horizontal area occupied by a group of air parcels over their surface per unit time. And d by dt of theta plus f is equal to 0. This is conservation of absolute vorticity. Air parcels conserving absolute vorticity following the motion are called constant absolute vorticity trajectories or CAV trajectory. Such air parcels, when move forward, the Coriolis parameter increases and theta has to decrease as the sum is a constant. Since relative vorticity is expressed mostly as curvature, the forward moving air parcels must lose cyclonic curvature and takes anti-cyclonic curvature. The converse is true for air parcels moving towards equator, takes cyclonic curvature due to conservation of absolute vorticity following the motion. I just mentioned about features of potential vorticity in the last class. Let us discuss further with a simple equation for the potential vorticity. The third, the potential vorticity is the ratio of absolute vorticity to the height of air column, that is theta plus f divided by h. From the continuity equation, 1 by rho d rho by dt plus del dot v is equal to 0. And for incompressible fluid, d rho by dt can be treated as 0. And hence the equation becomes dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. That is dou u by dou x plus dou v by dou y is the horizontal divergence capital D is equal to 1 by a dA by dt as per the definition, that is fractional rate of change of area. And hence dw by dz is equal to 1 by h dh by dt. So therefore capital D plus 1 by h dh by dt is equal to 0. That is capital D is equal to minus 1 by h dh by dt. So the vorticity equation can be written as d by dt of theta plus f is equal to minus in bracket theta plus f multiplied by dou u by dou x plus dou v by dou y plus tilting time plus solenoid time plus frictional time. As per the scale analysis, the last three terms are small compared to the divergence term. Accordingly, we can write as a first approximation as d by dt of theta plus f is equal to minus theta plus f multiplied by dou u by dou x plus dou v by dou y is equal to minus theta plus f multiplied by minus 1 by h dh by dt, and by simplifying on the basis of the Cochin rule of differentiation, we can obtain an equation for we can obtain an equation d by dt of theta plus f divided by h is equal to 0. As per the equation, the ratio of absolute velocity to the depth of air column or height or thickness of the air column is conserved following the motion. Here, theta plus f divided by h is called potential vorticity. And this potential vorticity is also expressed as theta plus f divided by delta z. Another form of potential vorticity is in bracket theta plus f multiplied by dou theta by dou z, where theta is the potential temperature. Next, let us discuss scale analysis of vorticity equation. Scale analysis is a convenient technique for the estimation of magnitude of various terms in the governing equation for a particular type of motion. In scale analysis, typical expected values of magnitude of field variables, amplitude of fluctuations in the field variables, and characteristics of length, depth, and time scales on which these fluctuations occur are specified. These typical values are then used to compare the magnitudes of various terms in the governing equation. Let us apply scale analysis to the vorticity equation by choosing characteristics scales for the field variables based on typical observed magnitudes for synoptic scale motions as follows. These are the synoptic, based on synoptic observation. I think I need not explain further. Here, dou phi by dou y is beta parameter and is observed magnitude for the mid-latitude region is 10 raised to minus 11 m raised to minus 1 s raised to minus 1, and density of air rho typical value is 1 kilogram per meter cube. We chose advective time scale since vorticity pattern tends to move at a speed comparable to the horizontal wind speed. Using these characteristic scales to evaluate the magnitude of the terms in the vorticity equation, we note that relative vorticity theta is equal to dou v by dou x minus dou u by dou y is less than or equal to u by L is approximately equal to 10 raised to minus 5 s raised to minus 1. Comparing with Coriolis parameter, we see that theta divided by f, that is relative vorticity divided by planetary vorticity, is approximately equal to Rossby number, that is 10 raised to minus 1. Thus, for middle latitude synoptic scale system, the relative vorticity is small, one order less than that of planetary vorticity. Hence, theta can be neglected compared to f in the divergence term. Let us consider the observed magnitude for various terms in the vorticity equation. I need not explain this particular step. In the last three terms, there is a possibility that the two parts of the term might partially cancel so that the actual magnitude is less than that indicated above. By comparing magnitudes of various terms, we see that this is true for the divergence term because dou u by dou x and dou v by dou y were not nearly equal and opposite. The divergence term would be an order of magnitude greater than any other term, and the equation could not be satisfied. The scale analysis of vorticity equation indicates that for synoptic scale motions must be quasi non-divergent for divergence term to be small. For balancing vorticity advection terms, we see that dou u by dou x plus dou v by dou y is less than or equal to 10 raised to minus 6 s raised to minus 1, so that horizontal divergence must be small compared to the vorticity in synoptic scale systems. Retaining the terms of the order of 10 raised to minus 10 s raised to minus 2 in the vorticity equation, we obtain as the first approximation for synoptic scale motion d by dt of theta plus f for the horizontal is equal to minus f in bracket dou u by dou x plus dou v by dou y. The above equation states that the change of absolute velocity following the horizontal motion is entirely due to divergence effect. This is based on certain approximation in synoptic scale motion and is not valid in the vicinity of atmospheric fronts. Next, let us discuss Vorticity advection. Vorticity advection is the transport of vorticity by the wind. The transport of vorticity by relative motion, transport of vorticity by relative motion means relative vorticity. So it contains shear term and curvature term. In addition to that, transport of vorticity by plant vorticity. So vorticity advection is the process in which wind carries air parcels of high or low vorticity to another region, causing changes in the structure of atmospheric pressure patterns. Vorticity advection is important in atmospheric dynamics as it leads to rising or falling pressure and associated weather phenomena like clouds and precipitation. On the other hand, clear sky situation. Vorticity advection plays a crucial role in the development and maintenance of weather systems, including cyclones, low pressure area, troughs, ridges, anticyclones, etc. Positive vorticity advection or negative vorticity advection results in upper level divergence on convergence and is closely linked to vertical motion. Now, I invite your attention to sinusoidal isobaric pattern at mid-latitude, mid-troposphere level with pressure, lower pressure in the northern region, higher pressure in the southern region. Accordingly, the isobar in the northern region has a value 554 millibar, or isobar with 554 hectopascal is in the northern region, and isobar with 558 hectopascal is in the southern region. And you can see two troughs indicate, you can see one trough indicated by red dash circle in the southern region with a plus mark at the center. Trough in the diagram, there are two ridge lines on the diagram marked by blue colored circle at the center with a minus sign. As you know, a ridge line is characterized by maximum anticyclonic vorticity, and hence instead of ridge, the blue colored dash portion is indicated by anticyclonic vorticity even though it is ridge lines. Similarly, the cyclonic vorticity maximum indicated by a red plus mark is a trough line in the southern portion. So this sinusoidal isobaric pattern contains two ridge lines in the northern region and one trough line in the southern region. And the negative vorticity advection is marked in a blue shader arrow mark in which convergence takes place, and convergence is indicated by winds are directed towards the isobaric pattern. On the other hand, in the right hand side, you can see the wind pattern is directed from a cyclonic maximum region towards an anticyclonic maximum region, indicated by red and rose color, and this is a positive vorticity advection region or cyclonic vorticity advection region, and this positive vorticity advection region coincides with divergence in the upper level. That is why the winds are directed away from the isobaric pattern in the diagram. Let me explain further features for the positive vorticity advection. Then I will explain the features for the negative vorticity advection. Positive vorticity advection occurs when cyclonic or counterclockwise vorticity is advected into an area of lower vorticity as indicated in the diagram. This is also referred as cyclonic vorticity advection. Positive vorticity advection is associated with surface convergence, upper level divergence, and rising motion, and capable of helping cloud formation and subsequent precipitation. Positive vorticity advection helps to maintain the surface low pressure system. Next, let us discuss features of negative vorticity advection. Negative vorticity advection occurs when anticyclonic vorticity is advected into an area. Here in this diagram, the negative vorticity advection is from a ridge line indicated by circular dashed curve to a tough line indicated by a circular red curve. I repeat, the negative vorticity advection or anticyclonic vorticity advection is presented in the diagram in the western side from a ridge line to a trough line by a blue shaded vector in which the convergence is indicated by winds converges towards the isobaric pattern. It is associated with sinking of air, convergence aloft, and surface divergence. And this type of negative vorticity advection results in clear sky situation and stable condition. I think I am ahead of time. I think it is better to stop now so that I can utilize more time for question answer. So back to Rohini for inviting questions. Thank you all for listening me.
Thank you, sir. Sir, do you want to present more like for 5-10 minutes or something?
I am ready to
Yeah, you
present
can.
more, but I am very particular to have maximum number of questions at the end.
At present, there it seems that there are no questions.
No,
So
at the end they will ask. Okay.
yeah. So
Yeah.
if you want to continue for 5-10 minutes, you
Yeah.
can, sir.
Let me continue about the basic and fundamental ideas about vorticity.
Yes, sir.
As I mentioned earlier, it is the rotation of air parcels in the air surface about vertical axis. Actually, we have rotation of air parcels in the vertical as well as in the horizontal direction. But the rotation of air parcels in the vertical axis is very important for the weather processes because it is closely associated with ascending motion of the air. When the air parcels are rotating about a vertical axis, there is a component towards center due to frictional force. This inward component gives rise to accumulation of air parcels in the central portion, and during the course of time this will give rise to ascending motion, and this ascending motion is very important for the weather processes when the air is sufficiently humid or rich in humidity. On the other hand, suppose an anticyclonic system prevails over a particular region. Because of the anticyclonic system, we can expect divergent motion near surface, and hence we can expect warm and dry air near surface. And in such a situation, we cannot expect development of clouds or weather system. That is why generally over the desert region, because of the anticyclonic system, warm and dry air prevails, and there is no possibility for the formation of clouds. Even though the rotation of air parcels in the horizontal direction take place, they do not have direct influence on the weather processes, but by the second term in the RHS of the Vorticity equation, that is tilting term or tipping term, if the wind pattern is favorable, the horizontal component of Vorticity turns into Vorticity in the vertical axis, and this can influence the weather processes if it is in the cyclonic direction. Generally, the influence of such a tilting term or twisting term is small in practical sense. Rather, in the Vorticity equation, the divergence term is one order larger than the other three terms, and hence we do not bother the tilting term, solenoidal term, and frictional term. Another point I would like to give emphasis is in the Cartesian coordinate system, we consider the velocity as scale of velocity. Scale of velocity is usually expressed as del cross V, and del cross V contains the rotational effect in the three principal axes. Since meteorologists are concerned with velocity in the vertical direction, we consider unit vector dot k dot del cross V, and is expressed as dou v by dou x minus dou u by dou y, and generally this relative velocity in the z direction is represented by the Greek alphabet theta. Actually, the Cartesian coordinate system relative velocity term theta does not specify the shear term and curvature term separately. But if we are very particular to obtain the magnitude of shear term and curvature term of relative velocity, we have to use the equation for relative velocity in the natural coordinate system, and from the flow pattern on the basis of curvature grid method, we can easily evaluate the contribution of shear term and contribution of curvature term for the relative velocity. In addition to the relative velocity, the planetary velocity is also important, even though the planetary velocity value is relatively small in the tropical region. It is almost zero in the equatorial region and exactly zero at the equator. Generally, for the formation of weather system, the initial torque must be sufficiently large as per the Gray's hypothesis, and the initial torque is given by absolute velocity, that is the rotational tendency by relative velocity and planetary velocity. In the middle latitude region, for example, at phi is equal to 43 degree north, the relative velocity value is 1 into 10 raised to minus 4 s raised to minus 1. This relative velocity value is equivalent to that processed by a tropical cyclone. On the other hand, in the equatorial region, the relative velocity value, the planetary velocity value is almost zero. So, for the formation of cyclone in the equatorial region, the relative velocity must be sufficiently large so that the absolute velocity must be sufficiently large to provide the torque for the initial rotational tendency for the formation of low pressure system, and hence the frequency for the formation of low pressure system over the equatorial region is very small compared to that in the mid latitude region. Since now time is 4 o'clock, let me stop for the time being.
Okay, sir. Before we go to the question answer session, we would take some photos. So I request everyone to please switch on their cameras. Tyagi sir, Ashwin. Tyagi sir, you there? Okay, we'll take one picture then when he comes. Mrunal, would you like to take picture? Okay. Okay. So now I would request Mrunal Naik from IITM Pune to please conduct the Q&A session.
Thank you, ma'am. Thank you, sir, for this wonderful lecture. There is a question by Jocelyn. Sir, will you please explain zonal motion of vortex formation process during onset of southwest monsoon?
Let me use the presentation, or let me share the screen again.
Yeah.
let me try to answer the question of Josen on the basis of the diagram in which the monsoon cloud band is center is around 15° north. Cloud band is originated at the equator region and is passing towards north, and the western component of monsoon cloud band center is around 15° north, and zonal wind is maximum around 15° north, and the zonal wind components are decreasing towards north and towards south. And I explained earlier the relative velocity in the region A can be evaluated from the equation dou V by dou x minus dou U by dou y. In this particular context, y component of velocity V is equal to 0, and hence theta can be evaluated as minus dou U by dou y, and becomes a positive quantity because minus sign multiplied by a negative quantity inside the bracket. So, or the region A, the relative velocity is a positive quantity. On the other hand, just south of the maximum zonal velocity, the relative velocity can be evaluated as theta suffix b is equal to 0 minus a positive quantity is negative. So, in the northern region A, the relative velocity is cyclonic. In the southern region B, the relative velocity is anti-cyclonic. And what I wanted to impress during the class was, in both cases, the velocity is along a straight line. Even though the flow pattern is along a straight line, we can expect rotational tendency and can be assessed as cyclonic in the northern region and anticyclonic in the southern region B, even though everywhere the flow pattern is zonally along a straight line. I hope the concept is clear to Josen and others, and I am ready to clarify further on the basis of sub-questions.
Thank you, sir. There is another question by Sandeep Kumar. He is asking what is the minimum and maximum order of magnitude for vorticity?
Actually, I do not know the minimum values for the zonal or meridional wind strength for the vorticity because I have not specifically examined the features, and hence I am unable to answer this particular question. And suppose Sandeep sends an email with further details of the question, I will try to answer as a reply to email within 1 week.
Okay, thank you, sir. So there are no further questions.
Okay, thank you, Mrunal. So before we go to the vote of thanks, which will be delivered by Ashwin Zadav, so I'll give some statistics. At present, the participants who have recorded their attendance is 110, and almost 80 participants have rated it as excellent to very good. So 80%, more than 80%, almost 85%. So thank you, sir. Now I request Mr. Ashwin Zadav from SPPU to please conduct vote of thanks.
Thank you, madam. On behalf of organizing committee, I extend my sincere thanks to everyone who contributed to the success of the 13th lecture in our weekly online lecture series of atmospheric dynamics and its application to climate sciences. We are especially grateful to Professor Someshwar Das, Secretary of SAMA, for his welcome address and insightful overview of this lecture series. My heartfelt thanks also goes to our distinguished speaker, Professor C.A. Babu from CUSAT, for delivering an enlightening lecture on vorticity equation in Cartesian coordinate, scale analysis of vorticity equation, the relation between cyclonic, anti-cyclonic vorticity advection. I would also like to acknowledge Dr. Rohini Bhavar for moderating the session and Ms. Mrunal Naik for efficiently managing the question answer segment. Additionally, I appreciate the guidance and support of the panelists and EC members. A special thanks goes to participants and attendees who joined us from across the globe and to the dedicated team members at Savitribai Phule Pune University for their valuable role in organizing this lecture. Thank you. Thank you so much.
Thank you, Ashwin. And I would like to make one announcement before we leave that next week there will be no lecture. Previously, it was planned that there will be an exam on Module 1 and Module 2, but we will have only one exam, which will be at the end of the lecture series. So it will be a rest period or for everyone to revise the previous lectures on 19th. So thank you, everyone.